It is the 22nd, well, it is 2025, October 22nd, approximately 8:08 a.m. Moving on to Chapter 3 on the historical context of quotient groups and homomorphisms as presented in Chapter 3 of Dummett and Foote. So let me just get my notes here. So before groups, it's not working right. Let's see a trash can around here. All right, let's put this over here. Get another marker. Okay, so before groups, also a bit of an update on the way that I'm going to be trying to approach this lecture series is that before I was trying to go and do an entire chapter and then all of the exercises in that chapter. So far as explanations are concerned, we'll see about that. I've got to do a lot more training on my memory, but for now, before groups, permutations and equations were those were topics of study, transitioning from the from the 1700s to the early 1800s. So Lagrange who lived mostly in Paris in the 1770s. '80s. He studied permutations of polynomial roots, isolating the parity of permutations so even or odd, and anticipating the sign homomorphism SGN such that S of n maps to plus or minus 1, and the alternating group. And the alternating group A of n, A sub n. Now, I'll erase this. His orbit stabilizer style of counting sets sets the structures of what would become Lagrange's theorem on subgroup indices and orders into play. Okay, now let's look at the birth of group thinking on top of all of that. So we're talking the early mid 1800s. So there's a lot to say on this. So I'm just going to start out with, well, erasing the board. All right. So Cauchy this is so roughly the time where Paris, well, Napoleonic, well, post-revolutionary / Napoleonic France was really still dominant. He deepened the theory of permutations. Proved what we call Cauchy's theorem, what we now call Cauchy's theorem. That is, if A prime P divides G, divides the order of G, then G has an element of order P and chapter 3 will present the abelian case. A bit early for pedagogical reasons, but yeah, so following this line, this historical line, we move on to Galois. Paris, 1832. What did he do? So he introduced groups. To encode symmetries of roots. Emphasized subgroups, stable under conjugation, invariant equivalent to normal, roughly equivalent to normal, corresponds to normal, congruent with normal, and used quotient-like reasoning. Now, is criterion for solvability. For solvability by radicals. Anticipates solvable groups via chains with abelian quotients. Okay. Now let's talk about systematizing subgroups. Normality and quotients. Late 1800s developments mostly. So first of all, we turn to the case of Jordan, last name Jordan, Paris, 1870. And in Teate de Substituciones, substitutions. If I say it in the most American way possible, I think I can get away with it. He formalized permutations. Invariant normal subgroups. Cosets. And laid foundations for the Jordan Holder perspective maximal normal chains and their factors. Okay. This thing is falling apart. Okay. And Holder, I barely know her, no. But Leipzig, 1889, proved the modern uniqueness such that any two composition series have the same multiset of composition factors. Up to order / isomorphism. and Dedekind where etc. Well, I say etc., but it's really just because there's so many that'll be part of this notion that I mentioned here in a bit in Germany from the 1880s to the 1890s that consolidated abstraction, standardized normal subgroups, clarified quotient construction. Constructions and popularized, so this is an important thing. That's not ideal, is it? Okay. I'll have to duct tape that. But they also popularized the notion of the normalizer, n sub g of h, and centralizer, c sub g of h, right? Okay. Now, moving on to where we get isomorphism theorems and the lattice viewpoint. Roughly around the 1900 to 1930s. So three isomorphism theorems were implicit in 19th century arguments. Used in refinement / common factor proofs. Special attention given to Emily Noether, who came from Göttingen in the 1920s and gave a general abstract formalization across algebra. Groups, rings, modules, yielding the modern unified statement of isomorphism theorems. And chapter 3 presents the group specialized forms of them, which we'll be getting into. Now, there's this thread of the alternating groups throughout the give me a moment. And the sign map. And that's a thread through the 1800s, which develops in tangent with what we've been mentioning as sort of a main line. And this is mainly from the fact that we mentioned earlier, Lagrange's parity in this context with the sign map arose, so from Lagrange's parity arose the sign map and that the alternating group is equal to the kernel of the sign, the map of the sign map. So the simplicity of A of n for n greater than or equal to 5 developed by the late 19th century with a sub 5 already in Galois' crosshairs. Becomes a pillar of finite group theory. Chapter 3 will supply the quotient and the kernel machinery underpinning with results to boot. Okay, so here's why these individual notions of chapter 3 matter. So, for one thing, homomorphisms make structure visible via maps, kernels, and images encode what is forgotten and what is preserved. Quotients are controlled collapses by normal subgroups they isolate new structure while returning a group law. All right, so let's move on to this. Erase this and go ahead and talk about why the isomorphism theorems matter. So, isomorphism theorems are bookkeeping rules that relate subgroups images and pre-images establishing, well, allowing for enabling clean diagram cases and classification steps. Lagrange and Cauchy tie counting to structure. So divisibility of orders forces existence of elements / subgroups of prescribed states, of prescribed sizes, sorry. All right, now let's get on to discussing the importance of Jordan-Holder. Jordan-Holder gives a canonical fingerprint up to order via composition factors. Guiding classification strategies. And now looking at parity and the alternating group. These provide a prototypical kernel / quotient narrative with wide ramifications. All right, now let's just go ahead and sum up the historical context here before moving into the main structural part of the work. shouldn't be here. There we go. What's that? Okay. So some anchor points here. So to boot, you have the 1770s to the 1780s. Paris, where Lagrange introduces the notion of parity and cycle thinking to this context. And subgroup order, divisibility, and its infancy. And from roughly 1815 to 1845 in Paris, Cauchy develops permutation theory. And introduces the existence of P torsion when P divides G, the order of G. And from roughly 1830 to 1832 in Paris, Galois introduces invariant subgroups and while invariant / normal subgroups solvable chains, quotient intuition, so and there's a few more points which I gotta get to for just anchoring this. A short little summary of the historical context, so to speak. And that is 1870 roughly, Paris, Jordan develops invariant subgroups. And puts it within the early Jordan Holder framework. In 1889, Leipzig Holder takes uniqueness of composition factors. Oops. To its modern form. And in the 1920s, and Göttingen, Noether, abstracts, abstracts algebra, no, but abstract isomorphism theorems across algebra. Okay, now that's the main takeaways of what historical context I'll provide for chapter 3. Well, let's get into the lingua franca of it all and the common words and tools of the trade, at least at least insofar as chapter 3 is concerned. All right, got about until 9:30 until this area closes up, so yeah, so the words, the axioms, the theorems, etc. of the basics of quotient groups and homomorphisms as they're presented in chapter 3. So first of all, let's look at a definition for kernel of a homomorphism. So a kernel of a homomorphism is this. Well, suppose we let phi be the map from G to H be a group homomorphism. Well, then the kernel of phi is equal to the set containing G within the group G such that phi of G is equal to the identity. Okay? Mentioned intuitively, it's like the pre-image of the identity, right? So just move these out of the way. Now, let's look at some basic properties of homomorphisms. Well, let's look at a proposition on that. So let's let phi be the map from G to H, be a homomorphism. Then for all G within the group G and N within the integers, we have that for 1, phi of the identity of G is equal to the identity of H. 2, that phi of g inverse is equal to the inverse of g, is equal to the inverse of phi of g, and phi of g to the n is equal to phi of g to the n, and the kernel of phi is a subgroup of g, and the image of phi is a subgroup of h. Okay, now let's look at a brief proof of this with some intuition. Intuition. So homomorphisms carry the group law across identities to identities. Inverses to inverses. Powers to powers. Kernels. And kernels and images. Inherit subgroup closure. So with all that in mind, let's get into breaking this down step by step. So for step 1, what we can find is that phi of 1 of the identity of g is equal to phi of 1 sub g dot 1 sub g, and this is equal to phi of 1 of g, so the identity of g times phi of the identity of g, because we're dealing with a homomorphism here. So phi of 1 of g is equal to 1 sub h by cancellation in h. Right? Okay, and for step 2, one sub h is equal to phi of 1 sub g. It's equal to phi of g to the negative 1, which is equal to phi of g times phi of g to the negative 1. So phi of g to the negative 1 is equal to phi of g to the negative 1. Right? The inverse, so phi of the inverse of g is equal to the inverse of phi of g. Yeah. Okay. Now for step 3, for n greater than or equal to 0, use induction with multiplicativity. So let's assume for the inductive hypothesis that, well, let's see here, the base case is true. If we set n is equal to 0 or n is equal to 1, that's going to be true. Moving on to the inductive hypothesis. Suppose phi of g to the n is equal to phi of g to the n holds. Then say we have phi of g to the n plus 1. That equals to phi of g to the n g, which equals phi of g to the n times phi of g. Which equals phi of g to the n phi of g, which equals phi of g to the n plus 1. Right, so for n less than 0, we combine step 2 with the positive cases. Positive case. So that is to say, so for step 2 we had 1 sub h is equal to phi of 1 of g, which is equal to phi of g to the negative 1, which is equal to phi of g to the negative 1. So phi of g to the negative 1 is equal to phi of g to the negative 1. So that's what we had for case 2. So with this positive case, yeah, so this is sort of our base case. For the negatives, then what we can do is expound upon it inductively with a little switcheroo here. We say, okay, for the inductive hypothesis then, suppose m is equal to negative 1, then we'd have, what is it, phi of g to the m is equal to phi of g to the m, and then proceeding along the same logic, as the first part of this sum. As earlier yields the m+1 case. Okay. So we have that for step 3. Now on to step 4. If x, y are contained within the kernel of phi, then phi of x, y to the negative 1 is equal to phi of x times phi of y to the negative 1, which is equal to the identity of h. So x times y to the negative 1 is contained within the kernel of phi. So it's closed under multiplication. And it's non-empty. Non-empty as the identity of G is contained within the kernel of phi. Now for step 5, if x is equal to phi of A and y is equal to phi of B, if these lie in the image of phi, then x, y, and all of this is to show, this up here is to show the kernel phi is indeed a subgroup of G. And this step 5 is to show that the image of phi is a subgroup of H. So if x is equal to phi of A and y is equal to phi of B lie in the image of phi, then x times y to the negative 1 is equal to phi of A, phi of B to the negative 1, which is equal to phi of AB to the negative 1, which is contained within the image of phi. And it's also non-empty, right? So and proceeding onward. To a definition of quotient group via a homomorphism. So if if the map phi of G to H is a homomorphism with kernel K equal to the kernel of phi, then the quotient group G divided by K has as elements fibers, that is the left cosets of K and G, and I should note multiplication is defined by, I'm going to go all the way out here, multiplying images in H it's the product of fibers above A comma B within H. The fibers above A and B within H is the fiber above AB. Right. Now here's a proposition. Fibers are cosets of the kernel. And let's get into what that means a bit more specifically. Let phi be the map from G to H be a homomorphism. With kernel K. Now, if x is equal to phi to the negative 1 of A is the fiber above A contained in H, and U within X, then X is equal to U multiplied by K, while UK, which is equal to the set containing little uk such that K within big K. Likewise, X is equal to big K U. Okay, now let's look at a proof of that. Well, let's start with the intuition first. So, for the intuition, elements mapping to the same A differ by kernel elements. Each fiber is a translate of K on either side. Now for step 1, if little k within kernel here, k, then phi of uk is equal to phi of uk, which is equal to phi of u times phi of k, which is equal to a dot 1 sub h, which is equal to a. So uk is contained within x, which implies u big K is a subset of x. And it's because of the fact that K was arbitrary. Now on to step 2. Let's go ahead and wipe the board. Now, if G is contained within X, then phi of, well, it's supposed to be a U of U to the negative 1, G is equal to phi of U to the negative 1, phi of G, which is equal to A to the negative 1 times A, which is equal to 1 of H. So U to the negative 1, G is contained within K, and G is equal to UK, little uk, which is contained in little u big K. So X is a subset of little u big K. And for step 3, I'm just going to point this out. The right coset statement is analogous. All right, now let's move on to another proposition. Now let's look at definition. Left and right cosets. So for n as a subset of G and little g as an element of group G, left coset is G big N, which is equal to the set containing little g, little n, such that little n is an element of big N, and the right coset is big N G, which is equal to the set containing N G such that N is an element of big N, and right coset. Whoops. All right, and how do I say this? Any element of a coset is called a representative. All right, so that's it for that definition. Now let's move on to a proposition. And the proposition is that cosets partition the group and this is basically, so we're going to be looking at the equality criterion. So let's put this a bit more specifically. So let's let N be a subgroup of G. The left cosets of N form a partition of G, and moreover, for U and V contained within G, UN is equal to V big N, so these are big N's here. If and only if V to the negative 1, U is contained within N. All right, so let's take a look at that. As far as a proof of that is concerned, or a proof sketch of that is concerned. So intuition, cosets are translates of a subgroup. They tile G without overlap. Equality means the representatives differ by an element of N. So for step 1 here, for each little g contained within big G, little g is equal to G dot 1, and that is an element of G of little g big N. So union of little g, the union of little g n all the way up to G, how do I say this? The union of little g of n with little g being an element of big G, the union of all of those, that's equal to big G. So let me just move on to step 2. So for step 2, by the way, I'm going to try to discuss everything in more step-by-step because those are easier to remember and it just works like a sort of algorithm for proofs in a way. But if, step 2, if little u of n intersects with little v of big N is not empty, take x to equal u little n, which is equal to v little m. Then u is equal to v m n to the negative 1, which is contained in v big N. And similarly, little v is contained within little u n. So little u n is equal to little v n. And for step 3, u big N is equal to v big N if and only if u is an element of v big N, if and only if u is equal to v little n for some n that's an element of big N, if and only if v to the negative 1 n is an element of n. So there you have it. All right. Now, let's look at another proposition here. Actually, I have about 9 minutes left. So yeah, so I'll say this will defined well-defined coset multiplication and criterion. So let's look at this. Let n be a subgroup of G? Well, for one thing, then, the rule open parentheses u big N, close parentheses, dot open parentheses v big N, close parentheses is equal to open parentheses u v close parentheses N is well defined. On left cosets, if and only if G little g and G little g to the negative 1 is contained within N for all little g within big G. and we have little n is contained within big N. So that's rule 1. Now let's look at rule 2. Now, if it is well defined, this is built off the previous rule. Then for 1, the set of left cosets a group with identity one big N and inverse open parentheses little g big N to the -1 is equal to g to the -1 N. All right, now how do we go about proving this? Well, for the intuition, let's say, well, changing representatives must not change the product. This forces stability under conjugation. By every G. For step 1, assume well defined. Take u to equal 1, and so. Okay, we're a bit out of time actually, so I'll continue this in the next one. And that is it for now.